Hello, dear classmates. Good day to you all. I am Fan Wuqing, and we are students from the graduating class of 2023 at ICJELIC. We haven't decided on a name for our group yet, but we will address that later on. During the first week of the semester, Professor Sabrina, our foreign instructor, shared with us a newly developed model. He invited us to experience and test it together, focusing on two main components, the ARMA model and Markov chains. The ARMA model was applied to sales data forecasting at Walmart supermarkets. The obtained prediction accuracy after comparing it with the result of the M5 computation astonishingly reached a top 10 level on the leaderboard in terms of performance metrics. We have also translated the R language implementation code of the ARMA model in Python. We will be synchronously uploading it to the Baidu Paddle platform for open source purpose, allowing interested individuals to further explore and understand the implementation. Regarding the integration of Markov chains and random walks, due to time constraints, Professor Sabrina provided us with a theoretical understanding of the model and the derivation of the fusion process. Before recording this presentation view, we independently engaged in further learning and supplementation. Next, my colleague Shen Bochen and I will proceed with the specific explanations.
Firstly, let's take a look at the autographic moving average model. The table displays the performance of the top 50 teams in the M5 uncertainty competition. Professor Sabrina, targeting the competition dataset, achieved remarkable results using a simple approach based on the ARMA model and employing the exponentially weighted moving average to forecast volatility. After comparison, these metrics consistently rank among the top performers on the leaderboard. On the WSPL 20 category, a score of 0.2763 was achieved, and in the WMSSC 20 category, a score of 0.8947 was attained. These scores surpassed the 10th and 35th position on the leaderboard, respectively. As Professor Sabrina put it, simple but efficient. Let's revisit the ARMA model. The autographic moving average model is a method that combines the autographic and moving average models to describe the dynamic variation in the time series data. Its basic form can be represented by the formula shown above. In this formula, P and Q represent the autographic and moving average orders of the model, respectively. Phi 1 is the autographic coefficient, theta 1 is the moving average coefficient, epsilon t is the independent error term, and yt is the time series data. When we consider a first-order ARMA model denoted as ARMA 11, its simplified form is represented by the formula shown above. In this formula, yt represented the time series data. Phi 1 is the autographic coefficient, theta 1 is the moving average coefficient, epsilon t is the error term as time t, satisfying a mean of 0 and a variance of sigma squared. The ARMA 11 model describes the relationship between time series observation and their previous observation in the immediate past moment, while accounting for the influence of random error terms. Furthermore, the ARMA 11 model can be described using a state space representation as shown above. This representation consists of two parts, the observation equation and the state equation. In this representation, mu t represents the state variable. The observation equation captures the relationship between observation and the state, while the state equation describes the evolution process of the state. In order to enhance the predictive accuracy of the model, it is crucial to find optimal phi and theta parameters that minimize the sum of squared prediction errors. To achieve this, determining the model parameters involves utilizing the maximum likelihood estimation method to find phi and theta values that maximize the likelihood function. The likelihood function is represented by the formula provided above. This function signifies the joint probability distribution between the model parameters and the observed values. A larger likelihood function indicates a better fit between the model parameters and the observed values. In our analysis, we iteratively expand the ARMA model as demonstrated above. This unfolding process aids us in gaining a deeper understanding of the dynamic nature of the model and the relationship between its parameters. As a result, we could enhance our comprehension and application of time series modeling. To estimate the variance of error values in the ARMA model with time-varying volatility, we employ the exponentially weighted moving average to forecast the model's volatility. In the formula shown above, alpha represents the smoothing parameter, where a smaller value leads to a smoother evolution of the variance sigma squared over time. By incorporating this volatility estimate into the likelihood function, we obtain the likelihood function as depicted above. To gauge the predictive error of the forecasting model, we employ the mean squared error as a metric. The calculation of MSE is as shown above. Its concept involves using the sum of squared errors as optimization object, which is a commonly adopted strategy. A lower MSE indicates better performance of the predictive model. When applied to ARMA model, for the first prediction, the MSE can be simply represented as the variance of the error, sigma squared. The calculation of subsequent predictions follow the formula provided above.
Here is our group's summary on the topic of binary Markov chains. To provide a more intuitive understanding of our summary, we first need to provide a detailed introduction to the relevant concepts of Markov chains. A Markov chain is a random process in probability theory and mathematical statistics that possesses the Markov property and exists within a discrete index set and state space. In simple terms, a Markov chain is initially a method for predicting the future state of an entity at a certain moment, such as whether a stock will rise or fall in the future. A Markov chain has three core elements: state space, memorylessness, and transition probability matrix. The state space represents the collection of all current and future states. Memorylessness, initially the Markov property, means that future events are completely independent and unrelated to past events. Instead, future events are only related to current events. Therefore, when predicting future events, we only consider the current state and not the past events. The transition probability matrix is used to describe the probabilities of transiting between different states in a random process. Each element in the matrix represents the probability of transitioning from the current state row label to a future state column label. Before introducing binary Markov chains, let's briefly discuss unary Markov chains. The concept is simple. It aims to determine the probability that the current state is A and the future state is also A. In contrast, a binary Markov chain is a type of Markov chain with a state space consisting of two elements. Since the future state of an entity may depend on the previous key states, we need to derive the expression for a case-order binary Markov chains. First, we obtain the first-order binary Markov chain, where it can be observed that the future state only depends on the previous state. Then we obtain the second-order binary Markov chain, where the future state depends on previous two states. Finally, we obtain the third-order binary Markov chains. By mathematical introduction, we can derive the expression for a case-order binary Markov chain. This section presents the expected expression, and this section presents the autoregressive expression. Since the relationships between different entities are often not binary, but rather multivariate, we need multivariate Markov chains to help us predict the states of entities. Therefore, we introduce the concept of vector Markov chains. Here is the preparatory work we conducted before applying mathematical introduction. By mathematical introduction, we derive the expression for a vector Markov chain as follows. The above is our group's summary on binary Markov chains. We apologize for any shortcomings and appreciate your understanding. That wraps up all the formal content. As a closing note, let me share some delightful quotes, Easter eggs, from our week together. Professor Srana has truly shown us what it means to be a sincere and lovable educator. Throughout this journey, we not only acquired knowledge, but also forged deep teacher-student connections. As the course came to an end, a heartwarming surprise awaited us. Professor Srana's wife and daughter, Carla, treated us to a delectable Italian meal. And that's not all. The charming Carla also graced us with her melodious singing. On the day before Professor Srana's departure, each of us got hands on in the kitchen, preparing a Chinese dish and inviting him to a dinner feast. As a gesture of gratitude for his guidance and dedication. In conclusion, we hope our course presentation has lived up to the expectations of our esteemed teachers. And to our dear Professor Srana, as you return to France, we wish you good health, smooth work, and perpetual happiness every single day.